right, I see the notification. And I'm going to get started while people are still coming in. I see the numbers stabilizing now. Okay, I'm going to get started. So good morning, afternoon, and evening, wherever you are. Welcome to Astrocheminar. Today we have two exciting talks. First up will be Connor Wright. Connor did his bachelor's degree from Berry College in 2017, and he's now a PhD candidate in the group of Professor Susanna Whitaker-Weaver in University of Wisconsin-Madison. Today, Connor is going to talk about extending the millimeter, submillimeter rotational spectrum of ground state pyruvic acid for comparison to astronomical data. So you can take over, Connor, whenever you like and share screen.
Great, thank you. All right. Okay, it is shared. Okay. Hi, everyone. Thank you so much for coming to our talks today. I'm very excited to be here talking to you about this project that we've been working on for a little while now, and are just now preparing to submit for publication. So hopefully it will be accepted soon, and you can read all the gory details that I leave out of this talk. So first off, why are we interested in pyruvic acid in the first place? Well, we know that large interstellar organics play a really vital role in the interstellar medium and the chemistry that happens there. The list of detected interstellar organics, of course, as I'm sure we all know, is growing probably as we speak. But more than that, pyruvic acid has some biological and even prebiotic relevance in the interstellar medium. We know, if you may have heard it thrown around in biology class, it is an intermediate in the Krebs cycle, where glucose is converted to energy in the body. But prebiotically, it's also a potential and theorized precursor to the chiral amino acid alanine. Some recent theoretical work has indicated that it forms on the mantles of ice grains of acetaldehyde and carbon dioxide through the radical-radical recombination of the hydroxycarbonyl and acetyl radicals. But despite all of this, and it being extensively studied theoretically, there's been no interstellar detection of it yet. So it's important for us to experimentally characterize it in the complete range that current ground-based far-IR telescopes operate in. So the first half of the talk, of course, I want to talk to you about our efforts in extending the actual experimental spectrum of pyruvic acid. So there has been previous work done on pyruvic acid in both the microwave and in the millimeter wave by the Keeschel spectroscopy group. Oh, excuse me, let me get a laser pointer going so I can point. There we go. Sorry about that. In the microwave, it was done from 10 gigahertz to 17.4 gigahertz in a cavity Fourier transform microwave experiment in supersonic expansion. And then in the millimeter, it was done from 160 gigahertz to 314 gigahertz in a static room temperature experiment. And as you can see here from this prediction of pyruvic acid at 300 Kelvin, the previous millimeter work stops right at the Boltzmann peak, right here where I put this line at about 314 gigahertz. And so there's lots of rich spectrum left to collect over here, which is what we aim to do. But I want to go back and talk still a little bit more about their previous work on this molecule, because it was really in-depth and well done. They also did an analysis of 3 different fitting programs that are available to us to fit these spectra. SPFit SPCat, which is the most widely used and standard program, and then Xiam and Airhem, which are 2 programs that are used to account for the presence of an internal rotor in a molecule. And as I'm sure you can see over here, pyruvic acid does have this methyl group right here that undergoes internal rotation and causes splittings of all the rotational transitions into A and E states. And therefore, you can fit those A and E states separately in SPFit, SPCat, as was shown but it is always better to fit it using Hamiltonians and programs that are designed to deal with this problem. And so they compared Xyem versus Airhem in fitting the pyruvic acid spectrum, and Airhem does the best in fitting to the experimental data. So what is our work focused on? We have the capability in our lab to measure from 90 gigahertz to up to 1 terahertz. And so we measured the complete spectral range of our capabilities for pyruvic acid in a standard long path length Beer's law flow cell experiment. We were able to add about 6,000 new transitions and assignments with a J-max of about 90. Of a J-max of 99. And like I mentioned, we used Airhem for that fit and prediction based on the recommendation of that previous work. So here is a schematic of our flow cell experiment. As I mentioned, it's a pretty fairly standard long path length experiment in a stainless steel flow cell with a base pressure of about 15 millitorr. And a sample pressure of about 15 millitorr, meaning a total pressure of 30 millitorr with sample present. We do flow the sample continuously rather than running it static due to low volatility of pyruvic acid. We generate our millimeter light with a Virginia diodes multiplier chain coupled to an Agilent microwave synthesizer. We collimate and focus our light using Teflon lenses, and we detect our light using an Insby hot electron bolometer. This signal is fed through a lock-in amplifier, which it helps increase our signal to noise and gives us our second derivative line shapes that you can see here. And all of this is recorded, of course, by a computer with a in-house scanning routine. So here is the collected spectrum from 90 gigahertz up to a terahertz. And I've marked out where the previously measured spectral range is. And you can see we have lots and lots of transitions that show up in our spectrum outside the previously measured range. Even in regions where it appears as if there might not be that much, that many spectral features, if we zoom in, you can see that there's lots of rich and dense spectra in there to assign. So here is the state of the Airhem fit, and I know this is a very large and very, very tiny table. So I'm going to zoom in on the sections to show you in detail so we can look at it and discuss. In the first section, I'm going to show you is the standard A, B, and C constants and the centrifugal distortion constants, and a comparison of that to the Keisha work in this column here. So as you can see, we have very good agreement in all of our rotational constants. And in fact, in several cases, we increase the precision of the rotational constants. As you can see here, that we adding a J-max up to 99 necessitated us to use octic distortion constants. And you can see those are fairly well determined values and errors. So moving on, now I want to talk about the tunneling parameters. So the tunneling parameters are the fit constants that Airhem uses to deal with the internal rotor splitting. And so as you can see here, we were able to use many of the same tunneling parameters as the Keisha work with fairly good agreement in several cases, and once again an increase in the precision of the parameters. And once again, because of our increase in quantum number, we needed to add higher order tunneling parameters to account for those as well. And those are all fairly well determined. So then some statistics of our fit. Our microwave RMS, which is the goodness of our fit, is below the experimental resolution of our spectrometer, that is 0.1 megahertz. As I mentioned, we were able to add about 6,000 new lines with a maximum assigned frequency of about 970 gigahertz, J-max of 99, Ka-max of 49, and a Kc-max of 99. So all of that to say that we were able to extend the fit up to 1 terahertz and make it increase the precision of the fit, as well as make it comprehensive in the complete range of far IR telescopes currently. So this allowed us to move on and do a fairly extensive astronomical search for pyruvic acid in many different astronomical sources. So previously in our group, there was before I joined, there was done a survey of about 30 astronomical sources, and these emission spectra were collected by the Leighton telescope at the Caltech Submillimeter Observatory between September 2007 and June 2013. 29 of these sources were previously analyzed in this paper that I cite here, Deep Broadband Spectral Line Surveys of Molecule-Rich Interstellar Clouds. And this allowed us to use the results of that previous fit to do a much more precise and in-depth, robust search for pyruvic acid in these 29 sources. Before I show you the results of this pyruvic acid search, I want to talk a little bit about the sources that we have the spectra of. And this is a lot of information, but I mostly wanted to show this to show that we have lots of different varying types of sources that we were able to collect the emission spectra of. So we have hot cores, hot carinos, class zeros, shocked regions, H2 regions. And so a very diverse and very unique set of sources that we have looked for pyruvic acid in. And all of these have varying luminosities and gas and dust masses, meaning that the chemistry is very diverse and unique in each source. I will mention that I've starred right here, Sagittarius B2N was not previously analyzed in the Deep Broadband Spectral Line Survey paper because of the chemical complexity and source kinematics and time constraints that were on that survey. So initial searches for pyruvic acid, as I mentioned, we included the results of that survey as previous fits and the functionality of that the program that we use to do these fits has. And we kept the parameter search space very wide just to see what we could get, even if it were to unphysical parameters. And unfortunately, all we were able to get was either no fit convergence, meaning it wasn't able to find any lines, or if it did find lines, it fit to completely unphysical parameters. And so no definitive detections were able to be claimed in any of those 29 sources. But we were able to do an upper limit analysis on all of these sources. And so what we did is we fixed the rotational temperature and the full width half max line width of pyruvic acid to the weighted average that was found using all of the previously fit molecules in that survey. We found the weighted average and we fixed those values and let the column density fit freely to find an upper limit for pyruvic acid in each source. As you can see, there are several upper limits that appear that are very, very low, meaning it's essentially, it's not there. But there are some, which I've highlighted here with red boxes, that have upper limits that are fairly reasonable. So essentially anything of 10 to the 10th inverse centimeters or above is a fairly reasonable column density upper limit. And from these, we undertook a by-eye search for any coincident line matches using from the in the fit simulation that is output from the fit program we utilize. And about 9, which I've highlighted in green here, about 9 of these sources appeared to have coincident line matches. However, all of these line matches were either heavily blended with previously fit transitions from known molecules in the sources, or they were at the noise limit for every source. So unfortunately, even with these reasonable column density upper limits, no definitive detections in any of these 29 sources could be claimed. So we moved on to our last hope, since Sagittarius B2N was not fit previously in the survey. However, we theorized heavily that pyruvic acid could be likely present in Sagittarius due to the presence of acetaldehyde and the hydroxycarbonyl radical. If you remember from my introduction, these are theorized to be precursors to pyruvic acid on ice grains. However, in order to look for pyruvic acid with any kind of confidence, the main spectral features from known molecules had to be accounted for first, which was already done for us in the previous 29 sources, but we had to do from scratch for this source in this project. Luckily, there is a wealth of literature on Sagittarius, and so we used two fairly extensive papers, Numelinol and Neal et al., to guide our fitting. And this gave us a list of 38 molecules with transitions in the range of our observations. And we started with the known weeds, such as methanol, methylformate, ethyl cyanide, dimethyl ether, and sulfur dioxide. And as you can see from this figure here, we were able to model the majority of the main spectral emission features in Sagittarius. Unfortunately, once we used these results to start searching for pyruvic acid on its own, it was unsuccessful. We were not able to get any physically meaningful fits for pyruvic acid on its own. But we proceeded with an upper limit analysis, once again finding the weighted average of the rotational temperature and line width, using these results that we have for the known molecules, and we get a fairly reasonable upper limit of 10 to the 15th. And you can see it plotted here. We see the pyruvic acid simulation with these parameters overlaid on the observations. But once again, all of these transitions, coincident line matches, were heavily blended with the already known molecules, and as you can clearly tell, is at the noise limit for the source. So no definitive detection in Sagittarius either, unfortunately. So just to wrap up, we were able to collect and extend the experimental spectrum up to 1 terahertz and refine the rotational constants. And then we were able to use that improved fit to search in 30 different very unique astronomical sources. Unfortunately, to no avail, but we were able to do upper limit analyses, meaning that if pyruvic acid is present in these sources, it's likely in very, very low abundance, and additional longer integration observations are required for definitive detection in any of these sources. So I'd like to thank specifically our previous lab member, Dr. Liu Yao Zhou, for his help with the observations and with the program, the fitting program that we utilized. And I'd also like to thank the entire Whittakus-Weaver group for all of their help and support, and both my committees at Emory University and UW-Madison, as we did move labs from Emory to UW last August. So both universities helped me in this project. And I'd like to thank you for giving me your time, and I'd like to open up for any questions.
All right. Thanks, Connor, for a nice talk. I see there's at least one question. I'll ask Professor Nesbitt to ask the question, if we can unmute his mic, please.
Good. So can you hear me now, Connor?
Yes, I can.
Good. Congratulations. It's really beautiful work and very nicely presented. I appreciate that.
Thank you.
I'm very much a newbie to sort of the procedure to which one applies laboratory spectroscopy to, telescope observations. But when you went through that exhaustive list of different sources and tried to look for upper limits on pyruvic acid and looking for matches, I'm wondering, how much do you utilize a very clear expectation for what relative intensities of lines would likely be, right? I mean, presumably, if you find a match that is obscured by some previous assignment or something like that, you certainly have some very strong sense of how intense other lines in your spectrum would end up being. And
Mhm.
shouldn't that add sort of a more physically intuitive constraint on the way you try and make identifications?
Yes. So I took it out in the interest of time, but the program that we use to fit the laboratory spectra to the observational data, it's called Go Basic, and it was a program that was designed by our group, and it does an LTE and Gaussian analysis on the observational spectrum, and you essentially feed it the molecular
Sorry, what is LTD?
LTE. I'm sorry, local thermodynamic
Oh,
equilibrium.
LTE. Okay,
Yeah,
yes. All right.
excuse me. Sorry. Yeah,
No, that's fine.
LTE.
Thank you.
And so it does this analysis, and you feed it molecular catalog information, such as the predicted catalog, the catalog file of the predicted spectrum, which comes from the laboratory fits, as well as the partition function information.
Okay.
And it varies the relative intensities of the catalog file prediction, and calculates a Gaussian line width, varies the line width of the Gaussian, and it calculates and it churns through different possibilities and combinations of that catalog file, and sees if it matches up with any peaks in the observational spectrum.
Okay.
And so with a new unknown molecule, since it's never been detected in the interstellar medium, it's really important that we have these previous fits that I mentioned with known molecules, because I could just drop in pyruvic acid and it could line up with a bunch of emissions in the observational spectrum that belong to, I'm just going to speak and say methanol, for instance, might be methanol, which we know is in these sources. Well, if we've already locked down and got a very reasonable fit for methanol, but for some reason it's not accounting for all of the emission intensity, well, that might be pyruvic acid. And then we can drop pyruvic acid in, and Go Basic will do all of that calculations for us, and tell us whether or not it is actually present.
Connor, thank you. Perhaps this Go Basic concept is well known to everyone else in the audience, but at least you've taught me something. Thank you very much.
Absolutely, yes.
Well, thank you for the question, and thanks for the talk and answers, Connor. I think we're going to go ahead in the interest of time. So thank you again for coming and giving a talk.
Thank you so much.
Wonderful. We're going to move to our next talk. The next talk is by Professor Ryan Fortenberry. Ryan Fortenberry has recently been promoted and granted tenure in the Department of Chemistry and Biochemistry in University of Mississippi, and is the graduate program coordinator for the department. He was previously at Georgia Southern University before joining UM. Ryan has earned his BS in mathematics and MS in communications from Mississippi College, and received his PhD degree at the Virginia Tech in theoretical chemistry. He was a NASA postdoctoral program fellow at the NASA Ames Research Center in Mountain View, California, where our paths also crossed. Ryan was recently the chair and past chair of the ACS Astrochemistry subdivision, and is currently the Ole Miss campus coordinator for the Mississippi Space Grants Consortium. Excuse me. Ryan was selected as the Virginia Tech College of Science 2019-2020 Outstanding Research Alumni Awardee, has been published in Scientific American, and is the author of Complete Science Communication, a text on how to write and talk about science both to expert and non-expert audiences alike. Ryan has dreams of climbing 50 state high points, and he has already climbed 34 of those. And today, Ryan is going to talk about the molecular building blocks of planets and other star stuff. So here is Ryan Fortenberry.
Okay. Thank you, Partha. I appreciate that introduction. I need to start putting that science communication blurb in there because now I'm worried that people are going to judge my presentations from now on.
Yes, we do, of course.
Very good. Well, thank you so much. Thank you for the invitation to be here. It's great to be back as a part of the Astrocheminar. Partha and the ACS astrochemistry officers have done a really great job of putting the seminar series together. And I was pleased to be a part of that now as I get to be a presenter. So let's talk about some molecular building blocks of planets and some of the crazy ideas that I've had. One of the things that I'm really hoping for in this presentation is that some of y'all will tell me I'm wrong and why I'm wrong so I can stop doing this crazy stuff and then go back to, normal things. But let's have a great conversation about it. So let me get going with the things that I want to share with you today. So in astrochemistry, we talk about elemental abundances and the things that we have to make molecules because we're chemists. And if we want to know what the molecules are that could be present out in interstellar sources, we have to know what they could be made of. And of course, this is from Ben McCall from a few years ago, where he put together the astrochemist's periodic table, where we have the sizes of the boxes are proportionate to the materials that we have, the atoms that we have out in various interstellar sources and astronomical objects. Lots of hydrogen, good bit of helium, and then there's everything else. I think I wrote in a paper one time that anything that's not hydrogen and helium are the scraps of the universe that we as chemists get to squabble over. But these scraps we can kind of break down into the remaining portion is seen here. We have a good bit of oxygen, some carbon, some nitrogen, and various other things. And this is kind of the universe as a whole from various different surveys. But different objects, of course, will have different abundances of things for various different reasons. And one of the things that we as astrochemists can do is to explore what these potential reasons might be. So let's look at one object, one of my favorites. Hopefully it's one of all of your favorites too. It's our beautiful Earth. And the Earth's mantle has an elemental composition roughly split up in this way. We've got tons of oxygen, a good bit of magnesium, a good bit of silicon, and some other things. But there's not a whole lot of carbon or nitrogen or some of the other volatile things. And there's lots of good reasons for this in geochemistry. But in thinking about this from an astrochemical perspective, all the atoms in the universe that aren't hydrogen and helium and a little lithium, most all of them were formed in the cores of stars or supernova events or neutron star collisions or various other exotic events that took place well after the formation of the universe. So the rocks that make up the Earth had to come from the atoms that were formed in these stellar nucleosynthetic processes. What's the relationship between them? Is there some molecule that could link these? And so that's really what I'm kind of interested in. Most of these molecules are difficult to create in the laboratory, or at least that's been the case in the past, and I have no experience doing laboratory astrochemistry. I'm a quantum chemist, and that means I'm going to have an equation. And we use the mathematics of quantum mechanics to dictate how we might be able to observe and predict the behaviors of these molecules where they could be observed. So we have the Watson Hamiltonian here, so our rho vibrational Hamiltonian, where you have our kinetic and potential terms, but it's the potential that we're really interested in. This is the difficult part for us to model. We choose to model this in what we call a quartic force field, a fourth order Taylor series expansion of the internuclear portion of this Hamiltonian, where basically we're doing numerical derivatives up to fourth order. A Taylor series, you take an infinite number of derivatives and you can exactly model your function. Here, we're just taking that up to fourth order because that's kind of a sweet spot between accuracy and the ability to actually have enough computational time to get through what we need to predict. The larger procedure, what we do is, for those of you who are familiar with quantum chemistry, or if you're not, the basic idea here is that we optimize the geometry. So we pick out a molecule. We start with the molecule that we want. We say, what is the spectrum of that? So we get as accurate a description of how those atoms want to relate to one another at an equilibrium state. Then from that equilibrium state, we do displacements. These are the delta values in that V equation that are above. And this is going to help us to define our potential surface, specifically our quartic force field. We calculate the energies at those points. We do a least squares fitting. Then I like to transform the coordinates. I got this from my postdoctoral advisor, Tim Lee at NASA Ames. Transform the coordinates because this makes them a bit more malleable. Then we use vibrational perturbation theory to describe what the fundamental vibrational frequencies are, as well as the rotational constants and some of the things that Connor was presenting earlier. What are we going to apply this to? Well, one of the simplest minerals, at least in my mind, are magnesium oxides. Remember in that plot, we had you had a lot of oxygen and a good bit of magnesium and some silicon. And magnesium is divalent, oxygen is divalent. So the simplest way in my mind to think about how we could combine these inorganic materials together that are really abundant in the earth to see maybe what are the molecules that could then go on to form these larger crystals in the earth. It's magnesium and oxygen. So we can do calculations on a diatomic species. Hope so. It's fairly simple. Magnesium oxide, though, when it gets to its crystalline form, is periclase, and it's these white inclusions. So magnesium oxide itself is not all that common. It took me a long time to find this picture. But as we'll see in a few minutes, it plays a larger role in geochemistry. The monomer for magnesium oxide, we were able to calculate with our highly accurate CCCR method. We also use another method called F12TZ, and I can explain that to you later in the questions if you care what those are. But we were able to calculate vibrational frequencies and rotational constants and compare with experiment, where we get in both the triplet and the singlet state, and we get pretty good comparison with experiment in a few of these. The dimer of magnesium oxide, I think, is really cool. So it's this D2H structure where we have the magnesiums and the oxygens making a diamond. Now, the interesting thing here is this molecule does not have a dipole moment, so it will not be able to be observed rotationally with microwave spectroscopy the way that, again, as Connor was talking about with his techniques earlier. So we need some type of infrared information. One of the things that comes out of magnesium oxide is that we have this really electronegative oxygen atom, and we've got this really electropositive magnesium atom. And the oxygen is like, give me all your electrons. The magnesium is like, please take them away. I don't have. And so it has this nice charge separation for when the atoms are moving. And this can give us some really large intensities. And so for the 3 vibrationally active modes for magnesium oxide dimer, we get large intensities. Now, what is large? Okay, this is always a question. We have to have a standard candle. Well, we talk about water in the atmosphere, and that's even why we have to fly SOFIA, because water is taking up so much of the infrared observational space that we can have. But the antisymmetric stretch in water at the same level of theory is calculated to be about 70 kilometers per mole. Here in magnesium oxide dimer, we're getting twice, 2.5, 3 times the intensity in this very small structure. And then we also calculated this for the trimer, where we're again getting some fairly large intensities too. Now, why does this happen? Why are we getting such bright intensities? So if we look at magnesium and oxygen, remember the oxygen is very electronegative and magnesium is electropositive. And so as those oxygen atoms in this one particular really bright mode are bouncing back and forth and back and forth and back and forth, the dipole moment is shifting dramatically such that we get this very large intensity. And if we have a very large intensity, according to Beer's law, the concentration doesn't have to be all that large. So maybe these really bright intensities will make these semi-exotic inorganic oxide type structures more observable for the next generation of space telescopes, like the James Webb Space Telescope or even SOFIA. So we took this idea for the magnesium oxide dimer and let's say, hey, let's keep these 2 oxygens on it and let's bring in some other things like some calcium and some phosphorus and silicon and such. And so we did a similar study for many of these inorganic oxide structures, again, where we have where we went across the periodic table. So things like magnesium, aluminum, silicon, phosphorus, sulfur, calcium, and even titanium. And what we were able to calculate from these were that we get, again, really bright intensities, some that are even 10 times the antisymmetric stretch in water, again, for Si2O2, P2O2, and Ti2O2. So we're getting some really bright intensities, some things that might make these molecules, even if they don't form, or even if they don't form readily, or even if they are quickly absorbed into something else, maybe these intensities would allow them to be observed. This made the cover of JPCA. Okay, what's another mineral that we have here on the Earth that's fairly common? Well, most of the rocks that we have are silicon dioxide. And here's a picture that I took when I was hiking the highest point in Texas, in Guadalupe Mountains National Park, where we've got some quartz. Now, of course, there's lots of forms of quartz, and one of my other favorite forms of quartz is this one, where we've taken quartz and ground it up, and that's sand. Of course, the monomer for quartz is silicon dioxide. It's similar to carbon dioxide, so we can calculate the vibrational frequencies and other spectroscopic constants for silicon dioxide. But we could also go to SiO3 or Si2O3 or Si2O4, which would be the dimer that we have here. And so we were able to calculate these frequencies. Comparison with experiment from a matrix isolation study is pretty good. And of course, we don't want it to be exact because we want our numbers to be slightly higher, mirroring the gas phase. But again, you know, the densities are okay. But one of the things that came out of this study that I really liked, that I thought was fascinating, was the monomer. That antisymmetric stretch across there is given here in red. It's a fairly large intensity. And then the black line is kind of the continuum that we would expect to see for some type of crystalline silicon oxide structure. And then when we go just from the monomer to the dimer, it downshifts. It gets to longer wavelengths, lower frequencies. And so just going from the monomer to the dimer, we're transitioning to longer wavelengths, lower frequencies. What happens if we go to the trimer, the tetramer, the pentamer? I imagine it's going to continue to downshift in some way. And then this leads to, for me, an interesting question of when does a structure like this, when does some crystalline glob of these nanoparticle type structure, when does that stop being a gas phase molecule and start being a solid? I mean, we could think of the Earth really as this teeny tiny little gas phase object in this vast vacuum description that is the larger universe. So it's kind of this philosophical question, but it is something that we could potentially define, and I would like to explore this in the future, where we're looking at how these nanocrystals are aggregating and getting larger, and the point at which the infrared spectrum stops changing for the addition of a monomer unit, in my opinion, would be kind of a place where we could demark between small molecules in the gas phase and crystals. But anyway, I digress. Okay, so I talked about silicon dioxide, and I also talked about magnesium oxide. So silicon oxide's everywhere, silicon dioxide's everywhere in sand. Magnesium oxide's not that common, but if we take these two and we add them together, we actually create an incredibly common mineral. And this is a magnesium silicate instantite. And the monomer of it looks like this nice ping pong paddle, or pickleball if you're into that these days. But the larger crystalline material is this brown crystal rock. We could take, this molecule is still small enough that we can use our quantum chemical methods to predict the vibrational frequencies and the intensities. And again, we get large intensities for many of these vibrational modes. It also is highly polar. This makes a whole new set of chemical issues, but it is highly polar. And this means that there could be a rotational spectrum associated with it. And here we were able to simulate that based on the things that we calculated. Now, if we take another magnesium oxide and we smack it onto our ping pong paddle, we get another ping pong paddle, but this one is the mineral forsterite. And forsterite is the most common end member. If you mix a little iron in the larger crystal, you get olivine, and that's this beautiful crystal on the right. And olivine and instantite are the most common minerals in the Earth's mantle. Yes, they're being convected around in a liquid form, but they are the constituent materials that make up most of the things that are not the Earth's crust or the denser core in between. We calculated a dipole moment. Again, it's very polar in this ping pong paddle, sound like Forrest Gump, ping pong paddle arrangement. And then again, we get these huge intensities for almost all of the vibrational modes that really we care to report. And notice that these vibrational frequencies, just like in the previous molecule, are all kind of further down into the mid and far IR, away from the regions that we typically associate with infrared spectroscopy. And I'll talk about that in a minute. Now, there is another isomer of the forsterite monomer, and that's where we get to a 4-coordinate silicon. It's about 10 kcals per mole higher in energy than our ping pong paddle C2V arrangement. And now we have a D2D structure. And this one has now one of the most intense vibrational frequencies that I have been able to see so far. And this happens when the magnesium and the silicon function as a unit, and they shuttle back and forth, or alternatively, the oxygen atoms are moving across the transverse of the molecule. So we get bright intensities, and then there's another one at 300 and another at 170. So, okay, this is great. We've gotten these monomers for these structures. We've gotten these intensities. What are some other molecules? I mean, we could go through all the minerals. There's thousands of them. We could go through all the minerals and try to calculate what their monomers were to see if we could, create spectral data that could be shared with both radio observers and new infrared telescope observers. but maybe we should start in a more informed way. So I had a poor student, bless his heart, calculated the bond strengths of all of the molecules from of all the atoms from lithium to chlorine. And we did this using homolytic bond cleavage, which of course is not always the best, the least energetic pathway to do this, but it was a place for us to start. And so what we did was we're creating what we're hoping to be described as single bonds, where we have the hydrogens on the outside will take the rest of the valency. So like the lithium dimer, for instance, is going to be Li, just Li2. But if we do lithium and beryllium right underneath that, then on the beryllium, we have a hydrogen on the other side. So we're using the hydrogen atoms to fill the valence. Most of the behavior that's in here is exactly what you would expect. As we cross the periodic table, the bond strengths get higher and so forth. But there are a couple of things that jump up that came for me as a bit of a surprise. The strongest, quote unquote, single bond on the periodic table calculated in this way is actually between beryllium and fluorine. And the next strongest is between boron and fluorine. Now, I was not expecting that, but of course, it makes sense. Again, electronegative, electropositive interactions. Some people have invoked a hard, soft, acid-base type discussion here. But the thing that is, I guess, fortunate for me from a computational chemistry perspective, as well as an astrochemical perspective, is that beryllium, boron, and fluorine just so happen to be the three least common elements in the periodic table before iron. They are so depleted that you have to get way down into the 5p block before you get to other elements that have similar abundances. And there's nuclear stability reasons as to why they're not all that common. But this means that from our chemical perspective, if we want to look at molecules that are probably going to form in the gas phase, we can throw these out because there's just not enough material there. Yes, we found molecules that contain fluorine, but on the whole, we can, as a first order approximation, say that there won't be many molecules containing beryllium, boron, or fluorine. Okay, so gotten those out of the way. The next strongest bond, again, omitting fluorine, comes in this valley right here. And it is magnesium to oxygen, silicon to oxygen, and then aluminum to oxygen. The strongest bond of the remainder is actually that ALO bond. And we have known for a long time as chemists that aluminum really likes oxygen and oxygen really likes aluminum. So this is not also that much of a surprise. But what did surprise me was the molecule that we were using to calculate this. The abundance, and I'll get to that in a second, the abundances of these strong bonds also happen to coincide, that's all I'm going to say, but they happen to coincide with the abundances of the most common elements in the Earth's crust. Is there a relationship? I don't know. Let's explore. For postulating such an abundance, they put this on ACS. Coincidence, rather, not abundance. They put this on the cover of ACS, Earth and Space Chemistry. So what is that molecule? That molecule, again, because we have our valency filled with the hydrogens, is this aluminum hydroxide structure. And there's not a whole lot known about it in the literature. Can we find, there are a couple of things, and I'll get to that in a second. Can we potentially find this molecule in space? So we calculated the vibrational frequencies and other spectral data. It has a mediocre dipole moment, about that of water, 1.2 to pi. And then we calculated vibrational frequencies, but it has some really bright modes. And the brightest vibrational fundamentals typically are corresponding here to those hydrogen bins on the aluminum. And again, these are in the mid-far IR. This molecule has been studied before. It was done from the perspective of from alternative fuel generation. Can we use alane, ALH3, and water to produce hydrogen? And so from this previous study from about 12 years ago, they were able to show that if you have alane and water, they will combine together. You got to go uphill, but you can come downhill. And when you come downhill from that submerged barrier, then you'll create this ALH2OH structure. Oh, that's pretty cool. But how does it go downhill in the first place? This is the beauty of it. Aluminum has, in alane and ALH3, it has that empty p orbital above and below. And aluminum and oxygen is like, hey, I got some electrons. You got a space to take them. Why don't you take my electrons? And so they form a dative intermediate. And that's what this WA structure is that they computed previously. And then it goes uphill And as it goes uphill, that's where a hydrogen from the alane and a hydrogen from the water come together, and they would prefer to bond together. And that's when you make an H2 and the H2 leaves. And so you get this AlH2, this really strong bond between aluminum and oxygen. And then you get H2 leaving. And if you think about this astrochemically, H2 is everywhere. You could think of it as the solvent of the universe. And so it's just like if you have a reaction in solution and you're making the solvent, we're making the H2 solvent in this reaction. Maybe this has something to do with the larger chemistry. We'll find out. And again, the structure for the product is what we had studied here. So it's not completely unknown. But I mentioned this really cool dative structure on the other side. Well, what does that look like? Well, it's a CS molecule where we have AlH3 goes pyramidal and our water comes in together and they make this dative bond. The bond strength here is not all that great. I think it's about 40 kcals per mole, but not insignificant. But this particular molecule, this potential intermediate in this reaction, which they have studied for the alternative fuel application, has a pretty large dipole moment. That's 1.6 to pi. That means that it should be rotationally active if it can live long enough and not vibrationally wreck itself or have the H2 fly off too quickly. We're able to calculate vibrational frequencies. Again, we're getting large intensities that are multiple factors higher than water. So let's go back to how this thing forms. This could also happen astrochemically, as I've mentioned a couple of times. So I wanted to know how it worked. Well, they had done a follow-on to say that, okay, if you have two alanes, two AlH3s, then you can make this nice little bridge structure at the bottom. So I got to thinking, I was like, okay, well, can we keep this going? Is this always going to, clearly this one's downhill. Is it going to keep going downhill, or are we going to have to cross some barrier? Is it going to stop at some point? So I came along with one of my students and we were able to use very much high level theory, explicitly correlated couple cluster theory, to reproduce what they already had computed. And the energies are roughly the same. But now what we have done is we have extended this well out where we've added more aluminums and more oxygens from water and alane here. So the red lines are for addition of water. I know. Blue lines are from addition of alane. What we see here is that if you add alane to the structure, you get basically no barrier to the addition, which is what we'd expected. And then you have to go up to the transition state. And each time you go up to the transition state, when you have an aluminum and a water bonded together, you're going to pop off an H2. But that transition state in every case is lower than the previous starting material. So it is downhill in every step. Yes, you have to go up a barrier. Yes, sometimes that barrier is pretty close in energy to the starting materials of that portion, but it's always less. And so it's up and down, it's up and down. It's just like going down a ski slope or a roller coaster where you ultimately create at the end of this process, and this was just an arbitrary choice of where we wanted to stop, you ultimately create this, I've lost it here, but Al2O3 structure. And Al2O3, yeah, we got some hydrogens on it. It's the hydrogenated form. But if we remember from general chemistry, Al2O3 is aluminum oxide, and it has a large crystal mineral that's corundum. And I took this photograph when I was visiting South Dakota, and we went to the Geology and Paleontology Museum, which is wonderful, there at School of Mines in Rapid City. But corundum, aluminum oxide, Al2O3, one of its polymorphs is ruby. And so we have shown in this work that if you start from alane and water, these two molecules that are fairly simple, then it will progress downhill until you can form the monomer, the hydrogenated monomer. But this process, probably you're going to have those monomers smashing into each other, and then they're going to aggregate, and the hydrogens are going to leave, and you're going to make H2, and there's going to be this plethora of H2 that falls out around it. And this happens in the gas phase, uncatalyzed. Could this lead to the formation of these types of minerals? Well, we've never found alane in space, Ryan. We've been looking for it for years. Well, it doesn't have a dipole moment. And maybe it forms and then reacts with water, because water is fairly common, very common in space. Maybe it reacts and does this process and starts to make these small nucleations. I don't know. I'm getting into speculation, but it's something that I like to think about. So if we go back to our periodic table of all these bond strengths that we calculated, and to the really strong ones, there's also another strong bond that we have between magnesium and oxygen. And this particular molecule is HMgOH. It is C infinity V. It is actually linear. It doesn't bend, which is kind of peculiar when you think about that oxygen. sticking out on the side, so it's not making that bent structure that we would anticipate. And that tells a lot about the electronic structure, which we could talk about later. How does it form? It actually does a fairly similar thing. So we have magnesium hydride, MgH2, which is a linear molecule itself. It associates with water, goes through this dative bonding, because now that magnesium has lots of p orbitals. It has at least 2 p orbitals that are available for bonding. And so the magnesium and the oxygen bond, we have the transition state, which again submerged from the top, where we create the H2, and then the H2 leaves and we go downhill a pretty good ways. And we can extend this into a larger network calculated at high level, till eventually we get to the magnesium oxide dimer that I talked about at the very beginning. Yes, it's hydrogenated, and I know that. But my thoughts here are that if you have this monomer, or the dimer, the hydrogenated dimer, maybe you bring in another hydrogenated dimer, maybe you bring in the monomer, or all these other things can happen where they start to click together once we have gotten into this nucleation process. And that's going to be something that we explore even more. One of the other things that happens here is that we also form the brucite monomer right here as well. And it's part of this process as it continues to progress. Okay, so we go back to this guide that we've created for ourselves now, looking at these strongly bonded molecules. And if we look at, magnesium doesn't just bond to oxygen, but it also bonds to nitrogen, and aluminum bonds to nitrogen too. What are some of these molecules? So I mentioned the magnesium oxide monomer, the hydrogenated form of it. We calculated vibrational frequencies, high intensity. If we move on to an amine on the end of it, large intensities in the mid to far IR. We do this for aluminum in the C2V structure. Lots of bright intensities in the mid to far IR. The dipole moments on these are a little disappointing. I'm not totally sure why. They're all fairly small, except for this AlH2NH2, this amine with the aluminum amine. But even that's not huge. But it is something that could be observed potentially with radio telescopes. Okay, let's go back. All right, got all of our big stuff. Well, aluminum also makes strong bonds with nitrogen and oxygen kind of bond to each other. What that molecule look like? So this is a C1 molecule. So actually the hydrogen on that nitrogen is sticking out of the plane coming at you. So we calculated the frequencies for this. The intensities aren't as great. They're not quite as high. The highest ones are about what you'd expect for the antisymmetric stretch of water. And this tells me that it's something about the sharing of the p block elements that, and we know this from general chemistry that, the electronegativities are fairly similar, and so they're not going to have as large of an induced dipole moment. I mean, it's still fairly large, but it's not multiple hundreds like we were seeing in some of the other ones. But this molecule does have a fairly large dipole moment, permanent dipole moment, making it more conducive for radioastronomical observation potentially. Okay, let's go back. All right, we got our strong bonds. We haven't talked about any of the things with silicon in it. Okay, so let's do that. All right, so we've got SiH3NH2, so silylamine or aminosilane, depending on what you want to call it. There are some gas phase experimental vibrational frequencies, and our numbers match up fairly well with those within about 3 or 4 wave numbers. Its dipole moment isn't that great, but one of the things that was nice about this molecule is it has the same connectivity as our AlH3 water dative bonded structure. So we were able to use similar materials that we had generated for that, but we get vibrational frequencies for these bending and stretching modes on the silicon portion that are fairly large. Silanol. It's surprising to me that silanol has not been observed in the interstellar medium. There's lots of conversation about this because we think about carbon monoxide, then going on to formaldehyde, and then going on to methanol. We would think a similar process would take place on dust grains, but that has yet to be documented, where we've seen this desorb into the gas phase. There's also strangely no existing vibrational infrared gas phase spectra for silanol. That was surprising to me that we could find in the literature. It has a decent dipole moment, but we've calculated some of these vibrational frequencies, and of course their intensities are similar, where we have these bright intensities. Now, I'm not an experimentalist. I don't know why it hasn't been done in the laboratory, and I'm not going to begin to speculate. I imagine that it's really hard, to be completely honest. Okay, so we've calculated all these molecules. We've gotten all this information. Is this really useful? Can we use this to observe such species in space? Well, the Butterfly Nebula, NGC 6302, from this beautiful Hubble image, and I'm think this one might actually be a real color image. Many of the ones we get from Hubble are false color. Again, y'all can tell me if I'm wrong. But anyway, about 20 years ago, they found the infrared signature of crystalline instantite, MgSiO3. That means that it's probably there in some crystalline form in either nanocrystals or maybe in some slightly larger structures. This probably indicates that there were rocky bodies around this star before it exploded in some shape, form, or fashion. Maybe asteroids, maybe planets. We're not, of course, there's no way that we could really know at this point, but maybe there were some rocky bodies that were there. The spectrum that they used to detect looks like this, and it's the bottom portions here where we have crystalline materials. So like I was saying, we typically think of the infrared region being about 12 microns and higher as being dominated by hydrocarbons. PAHs are probably one of the things that's there. And then from about 17 microns and lower, dominated by silicates because they're crystalline, they're heavier, they're going to have interactions within their crystal core that are going to reduce their kinetic energy and such, which shift the frequencies down. But the middle is kind of this place where, you know, maybe it's PAHs, maybe it's silicates. We're not totally sure. It's a bit far from where volatile species typically have really bright intensities for their vibrational modes. What possibly could that be? And so in this 12 to 17 micron range, which is about 833 to 588 wave numbers, I've got some ideas because one of my favorite molecules has a couple of really high intensity transitions in that range between 833 and 588 wave numbers. And then so does this molecule that I showed you, and this one, 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 and all of these that I have shown you today have notable intensities in this range that's a bit less well established as to what those types of molecules might be. Okay, so this plot looks, I'm almost done. This plot looks a lot like the one that I showed you previously, except now this is a follow-up study that we did where we're looking at double bonded species. So we've gotten rid of the fluorine and the halides altogether, but now we're having the valency of the hydrogens inscribed double bonding. So we have ethylene on here, for instance, in this portion. And if we go back to what our strong bonds were, you know, magnesium, aluminum, silicon with nitrogen and oxygen, the magnesium bonding actually goes down. What? I know, it's counter to what we typically think of. But if you think about the structure of magnesium and how electrons are in its divalency are not going to be like that in oxygen, but they're going to be on opposite sides, to bring them together to make a double bond on one side is going to be highly strained. So it's not going to be as favored to make such bonds. Aluminum, the bond strength goes down, and aluminum oxygen structure goes down by about 6 kcals per mole. So we'll call it flat. Now, when we go to silicon, especially with oxygen, and we make the silicon an analogy to formaldehyde, the bond energy goes up. Well, that kind of makes sense. Silicon's in the p block. It's going to have more availability to shift its orbitals around. So maybe that could have something to do with it. But this is kind of the side note. This was where we had such strong bonding previously, but when we increase the quote unquote bond order, when we decrease the hydrogens and the valency, yep, talked about that, the energy goes up somewhere else. And this is typically what we think of as happening in organic chemistry. Ethylene is going to have stronger bonds than methane does, by about a factor of 2 almost. And this is similar with carbon, with nitrogen and oxygen, as well as nitrogen with itself and also with oxygen. So now it's transitioning. When we get to higher bond orders, the bond strengths are actually shifting into more of the volatile species and away from these refractory elements that I've been showing you before. It gets even worse when we go to triple bonds, because now we just, really have the silicon left. The aluminum, I mean, if you look at the bond strength with aluminum and nitrogen in there, it's really small. It's 45. It's gone way down from what it was previously. Silicon is kind of in that mid-range. It's like, I'm still holding on, guys. It's saying to its refractory element buddies, but it can't compete with the volatiles. It absolutely can't compete with the volatiles. And so what I'll finish up with here today, and this is probably where I'm going to get in the most trouble, I would posit, based on these data, that in the primordial places where we think of the formations of molecules astrochemically, that PAH region might be because there's not a whole lot of hydrogen. And if you've got carbon atoms or anything flying around, those carbon atoms are going to see other carbon atoms and they're going to form strong bonds in various chemical processes. But they're going to be more available to form those strong bonds in regions where there's not a whole lot of hydrogen. If you start in your primordial region, and again, we can make PAHs, but if you start in the primordial region in something that's more hydrogen rich, where you have inorganic hydrides and water, those can react and react fairly quickly and downhill to start the nucleation process and to form H2 in these places where we can form larger inorganic oxides. And the crossover point is probably going to be in these small molecules and in these types of inorganic oxides and hydrides that I've shown you today. So that's kind of where our research is moving. We're doing lots of other stuff, but I would be remiss if I didn't thank all the wonderful students that I have here at the University of Mississippi. Here's a picture of my group from this summer. Here's another picture of my group from this summer where I get a water slide for them and we have a lot of fun. To kind of relax at the end of the summer. But I want to thank them. I want to thank the funding agencies. I want to thank all of you. And I want to thank all of the, in the invitation from the Astrocheminar folks. This is the book that Partha mentioned, and I'll leave you with this picture from the highest point in Texas. Thank you so much. I'll love to take any questions.
Thank you, Ryan. As always, very exciting and energetic talk. I really enjoyed that. I have a question for you comes from Dao Fu Yuan. He's, I'm sorry if I get the gender wrong. The question is, most of the vibrational modes, the difference between harmonic and anharmonic is about 20 wave numbers. However, for MGSI 05, it is about 56 for the V2. What would be the reason? And his general question is that, is there anything besides calculations, is there a general method to judge anharmonicity of different vibrational modes?
That's a great question. Yes, there's a wonderful thing to judge the anharmonicity, and that's quartic force fields and vibrational perturbation theory. The longer answer to that is it depends on what the electronic structure is. We typically think of, with Hooke's law, we have a mass and we have two masses and they're bouncing together and there's some constant that's proportionate for the spring constant. And we can apply that similarly, but the way that the electrons interact with each other based on what those atomic centers are and what the molecular orbitals are will dictate what those constants are. So K in Hooke's law is a lot like the F that I showed at the beginning when I was showing equations. And so it's going to change based on how the electrons are interacting is really kind of the shorter answer to that question. So there's not really a heuristic. We tried to do some scaling. If everything worked the same way each time, then we could just introduce scaling factors for the anharmonicity and we would get perfect predictions. But it shifts a little bit based on how the electrons are shared between the two atomic centers.
Okay, next one's not a question, but a request. Can you show the book again?
You bet. I would love to.
The next question is, have you considered, sorry, I lost that. Have you considered VSCF-based methods?
We have done, we've actually gone a step beyond that with VCI methods for some of these. The larger problem with those is that they're very costly. We could probably do some VCI, some VSCF. Haven't employed that yet. We haven't, the other reason is we haven't run into cases where that has appeared to be essential. So I've done some things with proton bound complexes where you have, like two carbon monoxides and a proton shuttling back and forth, and vibrational perturbation theory is going to fall apart for that. But in these types, and so you'd need to use VSCF. But for these molecules, they're very well bonded, and we chose this on purpose. They're very well bonded. The potential energy surfaces give us nice wells. They're not very flat. And so we haven't had a reason to do that yet. But you could, and it would be interesting to see how VPT2 and VSCF, VCI, or even V couple cluster were able to compare with the things that we had predicted. I don't think it would change a lot, also because the anharmonicities are going to be small because we're in that mid to far IR in small in an absolute sense, not a percentage. And so I don't know that we would necessarily need to invoke it, but it would be cool to find out.
Okay, great. I don't see any other questions, but I have one. I saw that you did the monomers. Let's say for olivine, you have magnesium, silicon, a few oxygens. The monomers, great. I would imagine you would want to do the dimer next. And what would be the path forward for that? You have, quartic force field with copper cluster wouldn't work there, right? So do you have a path forward for that?
Quantum computing. Cloud computing. Insert catchphrase for computational chemistry here. We could probably do it with DFT in a way that Cameron Mackey and Xander Thielens and Alessandro Candian have done that for PAHs. I have tried to do some of that with some scaling factors as well and gotten some mixed results that I don't quite feel comfortable publishing yet. But we would have to, the old saying is you can have it good, you can have it fast, or you can have it cheap, but you can only pick two. And so we have to have it cheap. And so we have to choose between good and fast. And so balancing between those really is what it comes down to. So, I mean, the anharmonicities aren't that big. The vibrational frequencies are an order of magnitude less than what we think of in hydride stretches. So we could probably reduce our level of theory and use something like DFMP2 or a density functional method that would work for these inorganic oxides to be able to do that. I've done some calculations on the dimer of the instantite with coupled cluster theory, and a single point there takes about a month. And we would be looking at something on the order of 100,000 points. And so cloud computing is the answer. So give me all, we could be like SETI, give me all of your processors. But yeah, we could expand it in that way.
All right. Thank you so much for the talk. Thank you, Ryan. Thank you, Connor, for these two great talks. And here we conclude another great Astrocheminar. I hope to see you again next month, November. I believe it's the 10th, when we have our next Astrocheminar, and we have two great talks. Yeah, it is the November 10th. Great talks lined up. So I hope to see you all. Thank you again to our speakers, and thank you all for joining. Have a great day.
Thank you.